Hello, 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 Arka sir.
Sir. Hello, sir. Afternoon.
Sir, we are just making as a co-host and presenter in 2 minutes.
Okay.
2 minutes, sir.
Sure, sure.
Everyone. Good afternoon, sir.
Afternoon, Parikshit ji.
Good afternoon, participant. For in the session number, I think 7 by Dr. Arka Prakash Majumdar, sir. So today, sir will be delivering on network protocols and IoT software. Before starting the session, I'll briefly introduce Dr. Arka Prakash Majumdar, sir. He has done BE in Information Technology from UIT, Burdwan University, MTech in CSE from NIT Durgapur, and PhD from in CSE from IIT Patna. His area of interest includes computer networks, wireless sensor networks, wireless ad hoc networks, and opportunistic networks. I'll request all the participants to kindly mute their microphone and keep only the microphone of the speaker on. Kindly, all of you do the needful. I'll request that host Triple IT Quota to kindly mute all the participants. Uh, Dr. Arka, over to you.
Yes, sir. Sir, there is only one problem. My share button is not activated.
I'll make sure. 1 second, sir. I'll make sure. Dr. Arka, sir, is it fine now? Over to you, sir. Yes, we can see your slides. It is moving.
Thank you, sir. Is my voice clear?
Yes, sir. Very much, sir. Yes, sir.
Okay, okay. So, thank you, sir, for
Ye-
nice introduction and for this session, giving me the opportunity to take this session. Good afternoon to all of you, the participants. I hope that you are having a very good learning time during this workshop. So what we'll be discussing in this particular session is bit of theoretical, and we are going to discuss the Internet of Things protocols and softwares. There are multiple protocols and softwares available. Some of them are already covered by Dr. Pilli in first day's lectures. So I will be covering other things except that. I will soon I will show exactly what we are going to discuss. So before we discuss the other things, let's say that we already know the previous traditional protocol stack or the existing traditional protocol stack that are being used in all the internet. Now, in the introduction of IoT, you might have understood that IoT is simply an umbrella that takes into account all possible communication strategies that we have, right? It's not only wireless, all the wired or any other type of communication that we are using nowadays, everything has become part of the IoT, because any device at any network has to communicate with any other device. Therefore, we cannot leave apart the existing protocol stack. It is also part of the complete network system. So, yeah, before moving ahead, let's say that we already are using TCP/IP model in most of the sessions, most of the networks that are being used, except some of the IoT specific or sensor node specific networks. We have also discussed that there is something called OSI model. We said that it's a theoretical model, but actually it was not. Anyone knows what happened exactly to this OSI model? Just for fun, has anyone read about exactly what happened to OSI model? If you have gone through OSI model, you will understand that this was not meant to be a theoretical model, and actually people paid a lot of money, invested a lot of amount to develop this OSI model. Now, basically, when you had this TCP/IP model, it was an incidental model. What we mean by incidental model is when the first form of network came, people developed something, developed models, certain protocols independently, and it became naturally like this. But later on, some people analyze that, okay, it's not exactly like that, and it has to be modular in nature. So you may have heard the term cohesion and coupling, right? High cohesion, low coupling. So that is a property between a modular programming. You may have read in software engineering. So what people try to understand is how should we divide these protocols so that each of the modules or the layers have high cohesion and low coupling among them, right? So we are trying to ensure minimal connectivity between each connecting layers. Right now in DC model, IP model, it is not like that. There are multiple parallel type of interfaces that are going on between multiple layers, right? When there are multiple APIs and multiple ways of communication, you are having higher coupling, because then dividing them properly will need more cross sections, right? So like if you want to divide, there are more lines to cut, and if you have a low cohesion, there are less lines to cut. I mean, when you are segregating the programs. But incidentally, this OSI model, because of high cohesion and low coupling, there are a lot of extra processes. There is one. Okay. And therefore, the resultant development was kind of bulky because of so much cohesion as well as slow. So anyhow, but theoretically it is better. Obviously, it is better than that. Therefore, practically it was not really implemented at the end of the time, and it became a theoretical model just to compare how good your existing protocol model is. But now we have to understand that this is no longer the only protocol stack. This is not the only protocol stack. There are other protocol stack being developed due to sensor network, M2M communications, and IoT. We'll come to that one after another. Right side, it is listed all the traditional protocols that we have been using till date. So this is what the relationships that we have right now. Most of the things are connected here. You can find out the data link and physical layer here. Data link and physical layer, these are the very, very important part. And you have 6-low pan over here running on top of 15.4 and Bluetooth. Then you have the RPL IPv6 together. You have TCP or TCP UDP or simply UDP. Then on top of that, you have the application layer protocols, HTTP or COAP or ACP2. On the other hand, in a completely different development mode, on top of 15.4, you have something called Zigbee, right? Right. So how much I'm sure that in the previous lecture, RPL has been discussed and 6LoWPAN is also being discussed, right? So other protocols are more or less same. COAP is also discussed. HTTP we are not going to discuss because it's a general mode. So what will be our line of discussion here is we'll be discussing on this physical and MAC combination, the layers, the protocols that we have, and we'll be discussing on some slides on Zigbee. So there are something called multiple access techniques which tells you what are the different ways of having a multiple access in the wireless medium. It's a general study understanding how you can actually access the media. We are going to omit that because of the low time availability, and we'll directly jump into the protocol standards 802.15, not only 4, but we'll discuss dot 1, dot 3, and dot 4. We'll discuss Bluetooth, but not Bluetooth 4, but 1.1, 1.1 and 2, and we'll also discuss Wi-Fi, right? So we'll be discussing this because these are the major parts of any IoT development. It is either Wi-Fi or you have a Bluetooth or you have 802.15.1 or 2.3.4, right? Now, when you're talking about 1.1 or 2, it is actually termed as 802, sorry, 8 not 802.15.1 is itself the Bluetooth standard. So we'll be discussing one after another. We'll start with the data link layer and physical layer, and gradually we'll cover this, and then we'll go to Zigbee and have a very small look on how it really looks like, how the protocol really works. Not every aspect we'll be discussing, but in a general understanding that what is different than the 6-LoWPAN RPL and COPE combination. So again, what we are trying to say is there are multiple ways of developing. Either you can go for uh, any combinations in this direction or in this direction, or you can have Zigbee as a complete separate development from network layer till application layer interfacing. Anyway, so we'll directly jump into the MAC layer protocols that actually gives you the access to the facility or the resource for the multiple users. So one major point here is you have to accommodate multiple users while accessing the media. There can be more than one, and there is always generally more than one user for the particular purpose. Now, this is the wireless space that we have. Now you understand that WPAN, WLAN, WMAN, which is the metropolitan area network, and WAN, which is the wide area network. These are actually talking about the radius or the range of the area it covers, right? So mostly we'll be discussing WLAN and WPAN. This will be our area of the data. You understand the position of 802.11 here. We'll be discussing 802.15.4 here. We have Bluetooth 802.15.1. And finally, we have the high rate wireless personal area network, which is 15.4. You can understand the speed of it. The highest speed that any of the one offers is 15.3. We'll discuss the purpose of each of them. Why do you need so many different types of uh, uh, protocols and their standards? If you look at the organization of 802, there are WLAN 802.11, the Wi-Fi that you are using, the wireless that you have in your phone, in your laptop, or in any other system. You have WPAN and many others, but these are not part of us. So we are already talking about the wireless parts. We have not discussed 802.3 Ethernet, 2.4 or 2.5. We are going to discuss basically on this particular domain. And yeah, this is how it is divided. Now, there are multiple groups and multiple subgroups, but yeah, we can move forward. So we'll start with the wireless standard 802.11 that is basically designed for all the small coverage areas and using the unlicensed spectrum. That means for using this particular Wi-Fi, that frequency that you are going to use, that range, you don't need a license for that. But for mobile phone, the cellular services, those spectrums are sold. You already probably know that, right? Selling of spectrum happens by the government, and multiple people goes for the auction and buys uh, the spectrum, right? So here the spectrum is called the ISM band, and it is an unlicensed spectrum, means you don't have to pay anything to use that particular spectrum. Anyhow, it has to have a very high data rate application, and it has to have a ability to integrate or application in a particular zone. The structure of the network of 802.11 that you have will look something like this. So what you have here is called a station or network station. You have a basic service set and you have a access point. So access points are the infrastructured wireless networks, devices through which all the endpoints or the clients are communicated, right? So under one particular axis, there are one or more network stations. If you are using your phone or laptop and you are connecting to one access point, then you are an network station or STA under a particular access point, right? All the nodes under this access point belong to a basic service set, right? So any other device, suppose there are other devices in this particular BSS1, in particular access point, all of them belongs to this BSS. So likewise, for each access point, there are separate BSS. Not necessarily, although sometimes what happens, if you have well structured access points implemented properly in your system, then multiple access points will carry the same name and same identity, creating a single BSS out of multiple access points. Sometimes you might see that in a particular building there are 4 access points, but when you search for a network, you see only one network. Means combining those multiple access points, you get a one BSS. Apart from that, there is a distribution system underlying that connects to the access point, and that distribution system can have multiple types of networks connected to them. Like here in the picture, it is shown that LAN connectivity associated with the access points. Anyhow, so this is the basic idea of the how the network structure is formed. This is an ad hoc mode. Ad hoc mode simply means that there is no one dedicated system just to let you communicate. In ad hoc mode, one of the most important thing is that all STA have equal priority. Okay, what does it mean? Previously, you have seen there is an access point. Now, if access point needs to communicate, needs to do something, access point can decide and capture the network because it has a higher priority than any other node in the network or in the basic service station. Now, that does not happen in the ad hoc mode. In ad hoc mode means none of them are confirmed and infrastructure, means things can change, right? Suppose there is one node here through which node 1 and node 3 communicates, but some other time maybe this node is no longer available, there is a fourth node available, therefore STA1 can communicate via this new node without any new configuration in the network, right? Which means any node can become a router or intermediate node that can send the data forward. This STA can itself work as an intermediate node to any other communication. What we mean to say is we don't have a specific node to handle the communication or work as an intermediary. So one particular set of nodes that are in the range and take part in the communication create the basic service step, right? So these are the different available frequency that we have. If you look at this, there are multiple standards that we have here. This is the basic standard of 802.11. It has support of either 1 Mbps or 2 Mbps, right? You have the frequency here, bandwidth available here. What modulation scheme? I hope that you have studied modulation schemes, different modulation schemes. So the modulation schemes that they are going to use here, channel architecture, which is here, and the range and the maximum power. You can find out that 802.11a works on a frequency band of 5 gigahertz, not 2.4 gigahertz. Both of them are ISM. Another new thing that you can find out is the channel architecture is different. Again, if you look at N and AC, both of them support 5 gigahertz right now. And as a rule of thumb, you understand that higher frequency band means you can achieve a better data rate. but the distance also reduces in most of the cases. I mean, if you're using the same configuration except the frequency band, then you are probably going to have a lower range than the lower frequency. So lower frequency, you can reach higher, and uh, but you might ask that how come then 2.4 gigahertz is for 20 meter, but here you have 35 meter? That also depends on the modulation schemes and the channel architecture that you are going to use. This is very, very important. The architecture that you are having and the modulation schemes that you are going to have has to be same, so that so as to compare. But if you look at the other things, like you look at AD, 802.11 AD, it is 60 hertz frequency it works, and the distance is 10 meter. The purpose of this we'll discuss later on. There is a very specific application for these things. There is something called AF, again, that works in a very low frequency range of 54 to 790, and you can find out the distance is greater than 1 kilometer, and it can reach up to 10 kilometers in multiple scenarios. If anyhow, so these are the more or less the standards that you have. Let's say that how much area does it cover for this particular scenario? Now the smallest area that any of this standards cover is 802.11, and it is a personal area network. It covers only a room, right? And the one specific application that it has is the multimedia communication. That means if you have a multimedia system, home theater system, you have a TV, you have a phone, you have a projector, and you want to communicate within the room but in a very high data rate, then probably you are going to have this particular 802.11 AD. General purpose, you are going to have 802.11a or AC, and then you have 802.11 B, G, and N for a higher distance. One particular technology between N and AC is AC has something called beamforming. Now, if you have not read about beamforming, I will suggest you and go and read what beamforming is, because we'll not have enough time to discuss beamforming here, more or less. But it's a very interesting strategy that if you have multiple antenna, you can actually propagate in a longer distance by synchronizing your multiple antennas propagation, allowing knowing the direction of the destination node, right? That is very, very important, knowing the direction. So yeah, I mean, N is also being used. Almost all the new infrastructure you will have N. The latest, some of the latest technologies will use AC, but yeah, N is right now the mostly used one. Yeah, this is more or less something that is not really part of it. So we'll directly jump to the work of the basic structure. Now we are going to discuss the basic 802.11 just because the technology is used in 802.11 basic. The first standard is the multiple IoT standard, which is a low powered mode and everything. They'll be using some of the properties of this basic mode. You can look at the other slides and you will be able to compare. We'll go to that. So 802.11, one mode of it is called FHSS, or frequency hopping spectrum, right? Now, why it is called frequency hopping? Because it has multiple overlapping channels. How many? 79 non-overlapping channels, right? Each of them are 1 megahertz wide, right? Now, how does it work? Suppose this is your frequency range and you have multiple channels like that. Each of them are 1 megahertz long. So there are such 79 such channels are available. Each of them has a width of 1 megahertz, right? But why is it called frequency hopping? Because each of the communication happens in one particular channel. Suppose this is channel number 0, this is 1, 2, 3, 4, 5, 6, and this is 78. So suppose at particular time t, your communication is happening on channel number 2. The next communication will not happen here. It will be a pseudo-randomly selected different channel, probably channel number 6. And after that communication, it will jump to a uh, separate channel, and it will jump through different channels for each burst of data. And how fast does it change? It has a specific rate, which is a 2.5 times per second, right? Which means 5 jumps in 2 seconds that are going to happen, right? So you are going to jump from one to another. Now you might say that what is the point of jumping from one to another? It is because suppose you are transmitting and there is some other listener. Suppose this is a receiver R is there, and there is someone else L who is a listener to it, who is trying to listen to the communication that you are going to have. R knows the sequence of channel hopping. Both sender and receiver knows the sequence of channel hopping, but the third party does not know that. If you are going to communicate in one particular channel, again, if you are going to communicate in one particular channel, then L, by searching through channel, will find out that okay, the communication is going through the channel number 6. So 6 will log into the channel number 6 and listen to the communication. Now, if you change the channel very, very fast from 1 to 6, maybe 1, 6, then 7, then probably 2, then probably 78, then probably 1, again, then 20 or something like that. For each fraction of packet transmission, L needs to search through this channels, all these 79 channels, to find out what is the particular channel on which this communication is happening. Now, thereby shifting through this channel in such a high speed ensures that your data is not listened by someone who is not unintended listener, right? So it protects you from data theft or anyone who is trying to listen to your channel. So that is one of the very, very important part of FHSS. Again, this was first proposed around the World War II, but it was not accepted at that time. But later on, the same idea was implemented by 802.11 and many others in a later stage of wireless communication. Anyhow, 802.11 says at least 6 channel hopping are required for a particular communication. But one problem is, you understand that if you are partitioning the complete available to 79 portions, then the available bandwidth for each of this channel is very, very less, like we have said, 1 megahertz. Therefore, and you are using only one part at a time, therefore at a time you cannot use more than 1 megahertz of frequency to communicate, because at a time you are using only one channel. There can be multiple channels, but one communication. So it is not spectrally efficient because you are not using your spectrum efficiently. Only one of 78th portion is being utilized. 78 by 79 portions are not being used. Sorry, 1 by 79 portion is being used and 78 by 79 portions are unused. Thereby, although it protects you from the channel theft of the data, but you cannot actually have a higher data rate through this. So what next it is going to be it uses is called a DSSS or direct sequence spread spectrum. It is called direct sequence means you are not going to have a pseudo random number to jump from one channel to another channel. The sequence is straightforward and in a sequential manner. So you are not going to jump the frequencies. You are going to be in a particular channel and you are going to transmit. So each of the channels are 22 megahertz. There are 3 non-overlapping channels. We'll look at that. Let's look at this picture first. So there are 11 channels, right, as centered over there. Only 1, 6, and 11 channel are non-overlapping, means you can use these 3 channels simultaneously by different users without any overlap, right? So that gives you the best possible usage of the network if you are going to use the frequency directly, the complete range of frequencies directly. Others are there just to provide the theft of it, like some of them are bit apart, some deflated from the starting range, so that if someone is listening here, it protects you from there. Anyhow, so these are the systems. 802.11 basic service gives you 2 particular channel access method or multiple access strategy. One is BPSK, the other one is QPSK. You can find out the chip phase. There is something also called QAM, which is a quadratic amplitude modulation, that has 3 things. Here chip means the bit that you are talking about. Phase means the phase difference of the particular signal that talks about this particular data. So there are 4 data. 00 means if anything that starts from 0, phase 0, it means it's the 00 data. 90 degree, any signal that starts at a phase difference of 90 degree is 01, and so forth. QAM has 3 things. It has this chip, it has its phase, and it also has the amplitude, right? Because each of the chips are going to have a particular phase as well as different amplitudes that are going to change the value. For example, you can have 2 amplitude levels. Like if you have something like this, one data can be like this, amplitude level 1, and another level can be here, 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 and here. So you can find out the amplitude level A1 is for this. The second signal is A2, but at the same phase. So at the same phase, there are 2 data at amplitude level A1 and A2. So this way, QM actually injects more data. Now, if you do that, you understand this, the size of this chip has to be 3-bit, right? Each of the chip will be 3-bit. It can be 000, 001, and so on and so forth. Anyhow, so QM is also there and being supported in most of the existing systems. The MAC layer have 2 particular services. One is asynchronous data service. The other one is time-bound service, which is kind of optional. The first thing is Asynchronous data service is most important, and you understand why is it asynchronous. Unless and until it is not delivered, it will try again and again. There is no time bound to deliver the packet, which means you are talking about a best effort communication from node 1 to node 2. Again, it has to support broadcast and multicast. If you have a time bound service, it is not a best effort. Why not? Because the packet, any packet, actually it's not packet, it will be frame. The frame will be discarded after timeout, right? So you have a time bound service. You have to deliver this in a particular time bound. Otherwise, you cannot do that. Again, you restart from the beginning. That is the basic idea. Again, it is called a point coordination function that allows you to have a time bound service. Now, point coordination service does not mean that it has to be a time bound service, but if you want a time bound service, you have to use the point coordination function. That's the only thing. Now, there are access methods, three types of access methods to be specific. One is DCF or distributed coordination function that uses CSMSEA. I hope that you have studied CSMSEA in a previous networking lecture or something. You can have DCF with RTS, CTS if you are really having a ad hoc kind of communication. This RTS, CTS will help you from the hidden terminal and exposed terminal problems, or you can have a PCF mode as we have discussed previously. Now, how does it look like? What is the relationship between them? These functions actually lead to interframe spacing times. Now, this IFS is essentially the interframe spacing times, right? So there are two functions, PCF and DCF, that leads to PCF IFS or PIFS, PCF interframe spacing and distributed interface spacing. Apart from that, there is something called SIFS. I think you have read that, short interframe spacing. There are other frame spacing itself, but before you start any of the communication or after any communication ends, you have this time bound. Why this SISF? Because in a particular communication, if you have more than one frames, and suppose you have 5 frames to send, then you don't fight for the channel again and again. What you do is you just simply wait for SIFS and start transmission. So if you have a continuous frames in a sequence, you wait for SIFS and start transmitting. You have a new packet to send, and you have not started sending yet, and you have a point coordination, means everything is synchronized by your access point. What you have to do is you have to wait for this amount of time, then sends if the channel is empty. After that only you send. So your contention really starts from here. Now, what happens if you have a continued frames, then this time gap protects you from others to start, because if you have a communication, before any new communication, you are going to start the next one. Similarly, DIFS is the least important communication here, where it is distributed and you have to fight for it. So if it is a DIFS, means if anyone does not have any packet and anyone is not using infrastructure mode, finally, the nodes that are going for a contention will start at DIFS, then will start contention, one will win, and they will capture the network and send the next frame, right? So that's why this 3 times are important, right? So it is important that SIFS must be greater than PIFS, and it must be greater than, I made it wrong. SIFS must be smaller than PIFS, which is done in turn must be smaller than DIFS to allow you time so that you don't have to wait unnecessarily, right? So this one decision is very, very important to allow who is the most important to send the next frame. If you are doing transmission right now, then probably you are the most important candidate to transmit. That's why SIFS is your waiting time. If you are going to start a new communication and you are synchronized by the access point yourself, then you are probably the next important candidate, and whenever your access point asks you to send after waiting PIFS, you start transmitting. After that, if no such candidate is available to transmit, then the channel is free up to DIFS amount of time. Again, these are the amount of times. Then all other nodes understand, okay, there is no other node to transmit. Therefore, we should contend and win the channel. So this is how the things occur, and this is how you select the channel one after another. Again, this is the idea of the contention window. So again, as I said, if the channel is free for more than DIFS amount of time, nodes understand that the channel is probably free and we should start fighting for the channel. And then, therefore, the contention window becomes very, very important. Okay, so this is the differ access. And therefore, each time they try to send, there will be a back of time, there might be a collision, and whenever there is a collision, there is a back of time. And after collision is resolved, one node gets the channel and start transmitting. And when the contention window ends, you stop transmitting and you send it to the next data. So as I said, each time there is a collision, there is a backup timer, and it's an exponential backup timer. How does it work? Look at the initial attempts. You generally say that there are 31 slots, means you generate a random number out of 31 and you defer that amount of time and transmit. And not transmit, you try to sense the channel after that. When it happens, if you see there is another channel, another one, and there is a collision, you don't do that. Then next, you double the range of the random number generator, right? So 31 means it's 32. So 2 to the power 4 is 16. 2 to the power 5 is 32. So it is 2 to the power 5 number of times. So increase the power by 1. Next is 2 to the power 6, which is 64. And you generate one random number out of it, and again try to defer that amount of time and transmit once again. There might be a collision and so on and so forth, but it does not increase unbounded amount of time. As the last two lines show, after fifth transmission, you reach 1023 slots, which means 2 to the power 10 value range. After that, you don't increase. So the maximum size is 2 to the power 10, the minimum size is 2 to the power 5. So this is how much. Then you continue generating random number out of 2 to the power 10 only and try to access the channel. Otherwise, then someone will get and someone will access the channel. So this is how your random number generator or backup timer works to access the channel in here. If you are using RTS CTS scheme for 802.11, you are probably going to use this time, and each time you receive a data, you do something called a NAV, right? NAV is a network access vector, or sometimes called network allocation vector. It is simply a vector that takes note or makes note of how much time the channel is going to be busy. Suppose this is a sender, there is a receiver, and sender wants to send the data and receiver wants to listen to the data. Very good. There are other stations, suppose other station number 1, other station number 2. Now station 1 is in the range of the sender. What does it do? It receives the RTS, and as you know, the RTS contains the total amount of time that is going to be captured for this particular communication. It reads RTS and sets in its own book, which is NAV, says that up to this time it is going to be busy. So what it simply does is it makes a note of the channel busy time, and it does not try to access the channel at that time, because if it tries to channel, then there's probably is going to be a collision, and it's no longer desired by anyone. So that is one very, very important point. Suppose node 2 is not in the range of the sender. What does it do? It can listen to the CTS, which is a clear to send packet, by the range of the receiver, right? So listening to the CTS, it understands what is the rest amount of time where the communication is going to happen, and it makes a note of that amount of time in its own NAV. So this is NAV of node 1, this is NAV of node 2, and it captures this amount of time. It is not anything else. It is simply a vector, means it's an array, one-dimensional array where the data is stored. So with that, it says that, okay, up to that time, I should not access the data. For example, suppose for this node 2, at this moment, there is a packet X to be transmitted. And this packet is at the network layer. Now, when the packet is a network layer and it asks the MAC layer that I need to send this packet to some node, what MAC layer says? MAC layer goes to this NAV and sees that, okay, the channel is busy during this time. It says that, hold on, the channel seems to be busy. I will try after the end plus DIFS time, right? So this is coded in the MAC layer in such a way that it will not try to access till this amount of time. After that, it will participate in contention once again and try to capture the packet to channel to send the packet. So any node that did not receive RTS or CTS is probably out of range of any of them. Then they don't have a conflict of interest or any conflict or chance of collision in that medium. So that's why there are two types of examples that can happen. One that receives the RTS, the other one that receives the CTS. You might ask why RTS come, CTS is not written over here. The reason is very simple. If you read RTS, then you mark your NAV then and there, and you go to low power mode and don't listen. Therefore, after this point, your network interface is down, thereby you cannot receive this CTS. So once RTS is received and you block your interface, you will not be able to receive anything else during the time. Now, sometimes I get a question that what happens if CTS is not sent back, which means the receiver is not ready to receive the packet. It might happen that it is already being communicated to someone else. Then what will happen to this particular node, because it has already received the RTS and not listening to the channel? The answer is simple. It cannot do anything. It will be in the low power mode. So even if the channel is free, it can't help anything, right? So once NAV is set, the node will be in the low power mode and will not try to access the channel for the duration. irrespective of whether the channel is actually being utilized or not. So this is how it is being coded. Yeah, there are certain problems, but it is what it is. This is another example, but with the fragments of packet. Again, it is very simple. If some of the nodes in the range did not even receive the RTS or CTS, it can happen because it's a wireless communication. It can happen that both the packets are lost and you are not able to listen. So each time you receive any other packet like fragment 1 or fragment 2, you can look into that fragment or acknowledgement and decide that, okay, up to this much time I have to stay. Suppose there is another possibility of NAV by set by uh, fragment 2, right? It is possible. So this will be NAV of fragment 2. So it tells you that looking at different packets, whenever you receive a packet, you read the header, you understand how long it is going to be blocked, and you set your NAV accordingly. And there are two plus points of this. One is less chance of collision. Obviously, when you are going to uh, set your NAV and you are not trying to access the channel, you are not going to interfere with the existing transmission that is being continuous in the channel. Therefore, there is a very less chance of collision once you set your NAV. This is the most important part. Secondly, there is an additional plus point. You save energy. You probably have heard a lot of time that energy saving is right now one of the very, very important things that we have to look for while designing any wireless communication. Now, this saves you a lot of energy because whenever it's not necessary, you know that the communication is not for you. You are not going to open the interface and try to listen. Why? Why it saves energy and why is it important? Because if you compare computational energy with communication energy, your communication energy is much higher than the energy required for computation. You can do a very small experiment. Suppose you have a mobile phone with you that runs for a single day on a regular use, right? You keep your Bluetooth on, your Wi-Fi on, and your network 4G is also on. Fine. For another day, you try to uh, turn off the all the interfaces, turn off your mobile, just put your mobile in aeroplane mode. I know that you will not be able to do that because a whole day without network is not easy. But if you get a chance and if you do that, you will see, even if you are doing something else, the same amount of screen on time if you have, the total energy consumption is going to be very, very less. And it is being proved at a lot of places that energy transmission and reception energy, which is the network connectivity in energy, is one of the biggest ones to capture energy. So if you can turn off or go to a low power mode for your interface for certain amount of time, it is likely going to save a lot of energy for your particular device. So that is this is more or less the 802 that 11's communication strategy. Yeah, there are a lot of difference. This is very small one, but yeah, we'll stop here and we'll continue with the other things. First, I will look for the chat box once again. Okay, so the other three things that we are going to discuss is part of the wireless personal area network or WPAN. There are three things: Bluetooth 802.15.1. Then you have HRWPAN, high rate wireless personal area network, 802.15.3. And then you have LRWPAN, which is low rate wireless personal area network, which is 802.15.4. There are other technologies also, like Enocean is there, Wetless is there, GPS GLONASS is there, WiMAX is there, NFC is there, RFID is there, and there are many other interfaces. But we are going to focus on these things because right now these are the mostly used technologies in the wireless after 802.11. Okay, so let's talk about the wireless personal area network. Obviously, personal area network means it has a short distance, and it is technically designed to support multiple PDAs, PC, cell phone, and so on and so forth. It must support ad hoc network, and if you open any of your phone, you have at least three radio interfaces in your phone: cellular, LAN, and Bluetooth must be there in your phone. Some of the phones will have NFC, as you might know, as you might have. So we'll start with 802.11, 802.15.1. The range is probably 0 to 10 meters for any WPAN. The speed has to be in somewhere at least between 19 to 100 kbps. And one of the most important thing is the footprint of your circuit. It has to be within zero point 0.5 cubic inches without the antenna, right? And it must be very, very of low cost. Now, Bluetooth interface, if you go and buy from a market, it has a very low cost and anybody can buy. But yeah, so that is one of the, and it has to support minimum of 16 devices. Say it's a minimum of 16 devices. There are changes in that we'll see at each of the points. So we'll start with Bluetooth, and you might know that it was started by Ericsson in 1994. It does not have anything to do with blue and tooth. It is not. So this is a wrong definition of Bluetooth. The name came from the Gomsen, who was actually a king of Denmark. And in 10th century, there are multiple Denmark tribes in their land, and they fought continuously, right? Each tribe had their problems with other tribes, and they continuously used to fight. Now, what Blatten did is he defeated all the tribes, and rather than creating a single tribe out of it, they tried to unify the tribe. They tried to become a mode of communication between the tribes, and they become part of it. So that is the point. Bluetooth does the same thing. There are multiple types of devices, and Bluetooth becomes a mode of communication, a simplification, or a mediatory to communicate between them. So that's why the name came from the Blatten, and with term it changed to Bluetooth. Okay, so the runestone was erected in 1999. What is a runestone? There used to be okay, before going to that, let's say that what are the companies? You can see Ericsson, Intel, IBM, Nokia are part of this. And there are many other promoters like Lucent or Aegir, which was part of Alcatel at one point of time. Microsoft, Motorola, they were part of this development and special interest group and promoters. And there are more than 2,500 members, like all of the communication companies become part of it. So this was the rune of King Bloodhound, right? So this was the imagery that tells that he has untangled and became part of the complete tribes in Denmark. Similarly, what Ericsson did is Ericsson created a similar rune like this, and this is in the Ericsson factory in Denmark. So yeah, this is the king, and this is the multiple types of device that are being communicated. Okay, so again, why we learned about FHSS is due to this. Bluetooth uses FHSS in its specific first specification or 1.1. In the similar manner, it uses 2.4 gigahertz as we discussed previously and 79 RF channels, 1 megahertz each. The same thing we have already studied in 802.11. So the same things happen. Now, the modulation scheme is a bit different. You understand that this is something called a GFSK modulation scheme, and transmission power is between 1 to 100 megawatt depending on the communication distance. It uses FHSS and time division duplexing, right? So what does time division duplexing means? Because it means that given a particular channel, you divide that into two times, probably time for transmission and time for reception. So technically what you mean is one is for downlink, the other one is for uplink. Sorry, I drawn the opposite thing. Transmission time is actually for the uplink and transmission time for reception is for the downlink. So you divide the complete time in two parts while you have the channel. One time is for uplink, the other time is for time downlink, which is called the time division duplexing. Duplexing means up and down together. And how do you achieve that? By doing time division. The hopping is bit higher than 802.11. We have seen that 2.5 hops per second, but we can see that for Bluetooth it is 1600 hops per second, right? And again, as I said, the hops happen depending on a pseudo random number generator, and it is known by both transmitter and receiver. Okay, so what do you know? Both transmitter and receiver shares the seed value of the pseudo random number generator, so that they understand which will be the next channel for the communication. Okay, so there are two types of communication. One is for the voice link, which is called SCO mode, which is synchronous connection oriented mode. Synchronous and asynchronous, right? And it uses FEC for the error correction. Retransmission is not present because it's a synchronous, and it has a 64-bit kilobit per second duplex, right? The other one for data link, you have to switch to ACL or asynchronous connectionless mode. This asynchronous connectionless mode can be either symmetric or asymmetric. Symmetric means where both the size of uplink and downlink are same. Size means the time duration I'm talking about. Actually, we'll look at that. I should have a diagram for the same. And asymmetric means where the uplink and downlink or master slave times are different. No worries, we'll discuss that. And the topology can be of two types. One is called piconet, the other one is called scatternet. We'll look at that. The left hand side is called a piconet. There are two types of device. One is master, the other one is slave. Slave is which one communicate with the master, and master is the node that coordinates all the nodes under him, right? So this is a particular node where you have more than one slave and exactly one master node. So this is called a piconet. But if you have a network of networks where one slave is common in multiple networks, suppose this is net 1, this is n1, this is in network 2, and this is network 3. This is the master of n2, this is master of n1. this particular node is common in N1 as well as N2. So if you have a communication here, if you have a communication from this node to this node, how the communication will happen? This communication will be communicated via this master node. They will communicate through this common node, and they will actually go back to their master node and back to the node. So what scatternet says, you can communicate among multiple piconets via common slave nodes, right? So this is a network. We'll see the same fashion in some other network strategies also. So this is more or less the idea of the scatternet, and scatternet is, as you can see, is one of the most important part for IoT, because you might have multiple networks in a particular area, and if you want to communicate, there has to be some way of communicating between multiple networks, not only through the master nodes. So what is highlight here is the node that allows you to do communication between multiple nodes is not necessarily a master node. A slave can behave as a gateway to the other network, right? So this is why the piconet and scatternet is different, and they are important in the wireless communication. And this is what your TDMA TDD is all about. The first one is the symmetric one. You can find out that any packet range or the duration that is marked as M is for the communication of master node. The nodes, the duration marked as S, this is transmission by slave, and this is by the master node. So what you see here for a symmetric is the amount of time given to master and the amount of time for transmission given to slave are exactly equal, right? But what happens in asymmetric? The packets or the durations that you have may be different, right? Like this one, this is for the master node. It is different than this. This is different than this. So there are actually three types of packet. One is depending on duration. Type 1 is one packet duration, and the second one is three packet duration. The third one is 5 packet duration, or one slot, 3 slots, and 5 slots. So this is a 5 slot packet or 5s packet. This is a 3 slot packet or 3s packet. This is a 1 slot packet or 1s packet. You cannot have a 4 slot packet, is not possible. You cannot have a 2 slot packet, it is not possible, and they are undefined by Bluetooth, right? So if you are designing a MAC layer protocol for Bluetooth, you have to keep or network layer protocol of Bluetooth, you have to take care of what are the frame sizes supported by the Bluetooth. So you cannot have any other size of information. So either 1 or 3 or 5. So that is one of the foundation by the Bluetooth. So there are 3 modes apart from the active modes. So one particular node which is not active must be of 3 types. One of these 3 types. One is hold, second one is park, third one is the sniff. Okay. Okay, so what is hold mode? Hold mode means you were transmitting, but there is probably another communication came up, and thereby you had to hold your transmission. So you are ready to transmit, but you are unable because another transmission is going on. So you are going to go for a low power device and wait for the communication to come back. The second one is the sniff mode. You understand sniff means you are going to try to understand what is going on, right? So you are going to sniff, right? So these are the modes that will come back at the intervals and try to understand what is going on. And finally, these are the park modes. Park modes are the devices that are not going to be used probably right now. And the park mode devices cannot directly transmit. Why? Because they will give up their address. As you know, address is one of the most important thing. Without address, you cannot communicate, right? So with this, let us introduce that there are two types of addresses in Bluetooth. One is the active member address or AMA, which is a 3-bit long. 3-bit means 8 unique addresses. All zeros is a broadcast. Therefore, only 7 devices are supported at a time. So therefore, only 7 devices can be active at a particular piconet, right? Part mode members have a new address called a PMA, which is a 8-bit address. Therefore, there is only 255 devices because one address will not be used, and they cannot communicate. So any device which does not have to communicate right now will give up their addresses, AMA, and go for a PMA. So if you have a device, Bluetooth device connected to your phone that is not being used, and therefore it will go for a park mode unless and until you try to come up with an application for that. And also it tells you that at a time your Bluetooth device can communicate with 7 devices, not 7, actually 6 devices. One is it itself. So that is one limitation of the AMA or number of devices that you can communicate. So therefore, these park node devices cannot participate in the traffic. So technically, there are 3 types of addresses. One is BD address or the device address, which are the MAC address, similar to the 48-bit IEEE MAC. Any other MAC, it has 48-bit BD address or the MAC address. Then you have already discussed that there is a active member address or AMA, which is 3-bit. And then you have the park member address, which is PMA or which has a 8-bit, right? So devices, all the devices will have BD address, and any communicated device, one of these two. So AMA or PMA, one of them. So at a time, any device communicating with a particular node or connected to a particular node has exactly 2 addresses. Okay, so if you go forward, there are piconet communications. Actually, this is the same thing we have discussed previously. So we'll skip this for the time being. So another scenario that we have not seen previously is where one node can both be a slave as well as a master, right? For example, let's look at this particular node. This is a slave for piconet 1, right? This is the network 1 and this is network 2. So this particular node is slave for piconet 1, but it is a master node for the network 2, right? So one device can be both master as well as slave in the particular scenario. So how does it manage the network scenario? One part, it can be a slave, then at the next point of time it can jump and become a master at the time. So this is when the node is a slave and when it is a master. So this is particularly for this node M2. So they have to communicate back and forth through the timeline. Once it will become a master, once it will become a slave, so that they can communicate. Okay, so let's go forward and move from 8.2.11.2.15.1. We'll go to 15.3, which is the HRW pan, which is a high rate wireless personal area network. Again, as I said, the data rate has to be very high, and uh, the distance has to be very low. I will just skip through this because this is not very important for you guys. But technically, this is going to replace the media cables that you have, like HDMI cable or MHL cable, which has to be a very high data rate cable. And if you want a wireless connectivity between the devices, 802.15.3 is provided to replace that particular. So one of the application is probably to replace the wireless 1394 bus, right? So this will become a wireless bus equivalent to 1394. So this new specification 803 2.15.3a is actually a wireless bus for the 1394 specification. So we'll directly jump to the last specification of the MAC layer that we wanted to discuss, which is a WPAN or 15.4, which is actually adopted by Zigbee Alliances, IPSO, Thread, and Google and everything. Again, the previously like that, it has to be a small size, low cost, high reliability, long battery life. These are all some small specifications for the WPAN, and it is same for them. This is where the implementation is all about. You can find out the Bluetooth to be here, and on top of Bluetooth also you can have 6LoWPAN. So anybody who thinks that 6LoWPAN can only work on 15.4, it is not right. Normally it can be on top of Bluetooth also, right? Similarly, you can have 6LoWPAN on top of 15.4, or you can directly have your Zigbee protocol suite running on top of 15.4. Now we'll come about IPSO and Zigbee that can run on top of 6LoWPAN. These are the market value. We'll skip that. There are certain things. There is a comparison between the multiple formats or the standards for 15.4. We'll skip that. I will share the screen. These are just the block of information. You can go through this. Okay. One of them is important is 15.4F is an alternate physical layer using active RFID. Again, so 15.4 does not necessarily have a RF physical layer. It can have a RFID physical layer also, right? Not only the 2.4 gigahertz only. Okay, so this is a comparison of the Bluetooth versus IEEE 15.4. I will skip that for the time being because we have very low time. So this is the implementation and integration of multiple protocol stack. If you remember at the beginning, we said that there are multiple protocol stacks right now possible with the advent of this particular physical and MAC layer. So look at that physical and MAC layer. For both the cases, we are assuming that we are talking about 15.4 MAC layer and physical layer only. So if you look at IPSO, you have 6LoWPAN on top of that, then IPv6 and RPL. Similarly, if you have Zigbee IP, it's similar to that 6LoWPAN IPv6 RPL, and you have a COAP or running on top of it. But if you see that before application, you have a Zigbee application framework running on top of COAP. Now, if you compare this one particular combination, you have already done in your previous lecture, right? So the alternate of that is having Zigbee security and Zigbee network layer on top of directly 15.4. There is something called Thread, which is developed by Google and right now adopted by ARM, Intel, and Google itself. What it simply does is it does not use RPL, but it uses a thread routing protocol on top of IPv6. It's a different routing protocol than RPL, but they say that. And there is another security protocol called MLE included by Google in top of that. Now, thread does
Hello, hello, Arka sir. Hello, hello,
Yes.
hello, Dr. Mishra. Hello, hello. Is I'm audible?
You are audible, sir, but Mishra
You are
sir
audible,
is
sir.
not there.
I'm audible. I think something has happened. Host कैसे change हो गया?
Dear sir, what's your instruction, sir?
Hello, Dr. Satan, can you make me host? Dr. Satanan, I think it will go. हाँ वो
Hello,
hello.
Dr. Sanan Mishra is speaking here.
Can you make me host?
Okay, sir. Doc- okay, sir. Sneha, sir.
तुम कनेक्ट करो. ये आ गया क्या? हाँ आ गया.